Right now, as you're listening to these words, preparing perhaps for sleep, something rather extraordinary is happening inside your skull, behind your forehead, beneath the gentle curve of your cranium. Your brain is preparing for one of the most important processes of your entire life, a process so crucial that without it you would die within days, yet so mysterious that we only discovered it existed a few years ago. For the longest time, scientists had a problem. Every other organ in your body has a cleaning system. Your liver filters toxins from your blood, your kidneys remove waste, your lymphatic system, that network of vessels and nodes, acts like a biological sewage system for most of your body, carrying away cellular debris and metabolic waste. But the brain seemed to have no such system. This was puzzling, even troubling. Your brain uses about 20% of your body's energy. Imagine a city that consumes a fifth of the national power grid. With all that metabolic activity, waste products must accumulate: dead cells, protein fragments, toxic byproducts of neural activity. Where does it all go? For decades, the answer was essentially, we don't know. The brain was like a house with no garbage collection, a factory with no waste disposal, a city with no sewers. Then, in 2012, a team of researchers at the University of Rochester made a discovery that changed everything we thought we knew about sleep, about the brain, and about some of our most feared diseases. They discovered that your brain does have a cleaning system. It just only works when you're asleep. They called it the glymphatic system, a play on glial cells and lymphatic system, and it's one of the most elegant and essential processes in your body. Every night when you drift off to sleep, your brain transforms into something like a biological dishwasher, flooding itself with cerebrospinal fluid that washes away the day's accumulated waste. It's happening right now in the heads of everyone sleeping within 1,000 miles of you. It will happen to you tonight. But here's what makes this discovery even more remarkable. Some of the waste being washed away includes the very proteins that, when they accumulate, are associated with Alzheimer's disease. Every night, your brain is literally cleaning out the substances that could fog your memories and steal your mind. Sleep isn't just rest. It's renovation, restoration, a nightly salvation from the slow accumulation of neural toxins. To understand this nocturnal cleaning crew, we first need to understand what makes the brain so special and so problematic when it comes to waste management. Your brain is, metabolically speaking, a furnace. Despite making up only about 2% of your body weight, it consumes 20% of your oxygen and 25% of your glucose. Every second, billions of neurons are firing, each spark of activity requiring energy and producing waste. It's like having a city of 86 billion residents, all working around the clock, all producing garbage, all needing their streets cleaned. But the brain faces a unique challenge that other organs don't: the blood-brain barrier. This is a highly selective membrane that wraps around the blood vessels in your brain, acting like an incredibly strict border control. It prevents most substances in your blood from entering your brain tissue. This is usually a good thing. It keeps out toxins, pathogens, and large molecules that could damage your delicate neurons. However, this same barrier that protects the brain also isolates it. The lymphatic system, which cleans the rest of your body, can't penetrate the blood-brain barrier. It's as if the brain lives in a gated community so exclusive that even the garbage trucks can't get in. For over a century, neuroscientists assumed the brain must have some way of dealing with waste, but they couldn't find it. They knew that cerebrospinal fluid, the clear liquid that surrounds the brain and spinal cord, must play some role, but the mechanism remained mysterious. The brain seemed to violate a fundamental rule of biology. Every living system produces waste, and every living system must have a way to remove it. The mystery deepened when researchers realized just how much waste the brain produces. Proteins like amyloid beta and tau are constantly being generated as byproducts of normal neural activity. These aren't inherently bad. In fact, amyloid beta might have antimicrobial properties, helping to protect the brain from infections. But like everything in biology, the dose makes the poison. Too much accumulation, and these proteins begin to misfold, clump together, and form the plaques and tangles characteristic of neurodegenerative diseases. The breakthrough came from an unexpected source, new imaging technology, that allowed scientists to watch the movement of fluids through living brain tissue in real time. Macon Nettergaard and her team at the University of Rochester developed a technique using 2-photon microscopy that could peer deep into the brains of living mice and track the flow of fluorescent tracers through the tissue. What they saw was astounding. When the mice were asleep, cerebrospinal fluid began flowing through the brain tissue itself, not just around it. The fluid moved through a previously unknown network of channels, washing through the spaces between brain cells like water through a sponge. Even more remarkably, this flow was not random. It followed specific pathways, moving in alongside arteries, through the brain tissue, and then out alongside veins. The channels themselves were formed by a type of brain cell called astrocytes, star-shaped cells that were once thought to be merely support structures for neurons. These astrocytes have special proteins called aquaporin 4 water channels positioned at their end feet, the parts that wrap around blood vessels. These channels act like gates, controlling the flow of fluid through the brain. But here's the truly mind-blowing part. This system essentially shuts down when you're awake. During waking hours, the spaces between brain cells are relatively tight, compressed. The cerebrospinal fluid stays mostly on the outside, in the spaces around the brain. But when you fall asleep, something remarkable happens. The brain cells actually shrink, reducing their volume by as much as 60%. The spaces between cells expand, and suddenly, the cerebrospinal fluid can rush in, flooding the brain tissue and carrying away waste. It's as if the brain has two states, a working state, where cells are swollen with activity and the streets are narrow, and a cleaning state, where cells contract and the streets widen to let the cleaning trucks through. You can have one or the other, but not both at the same time. But why does this cleaning system only work during sleep? Why can't our brains clean themselves while we're awake? The answer reveals something fundamental about the evolutionary trade-offs that shaped our minds. During wakefulness, your brain is in production mode. Neurons are firing rapidly, processing information, forming memories, generating thoughts. This requires the cells to be in close contact, with narrow spaces between them that facilitate quick communication. Neurotransmitters only have to travel short distances. Electrical signals propagate efficiently. The brain is optimized for performance, not maintenance. The energy requirements for this are enormous. The brain during wakefulness is like a city during rush hour. All systems are go. All resources are dedicated to keeping traffic moving, keeping the lights on, keeping business running. There's simply no capacity for major maintenance work. Sleep represents a fundamental shift in priorities. The brain switches from production to maintenance mode. The same energy that was being used to process information and generate consciousness is redirected toward housekeeping. It's like a city that shuts down at night, so the maintenance crews can come in. Street sweepers, garbage trucks, repair teams. The shrinkage of brain cells during sleep is controlled by neuromodulators, particularly norepinephrine. During wakefulness, norepinephrine, also known as noradrenaline, keeps brain cells in their swollen active state. It's one of the chemicals that keeps you alert and focused. But during sleep, particularly during deep slow-wave sleep, norepinephrine production drops to almost zero. Without this chemical signal keeping them inflated, brain cells relax and contract. This creates a dramatic increase in what scientists call the interstitial space, the gaps between cells. During wakefulness, this space accounts for about 14% of the brain's volume. During sleep, it expands to 23%. That might not sound like much, but it represents a 60% increase in the space available for fluid to flow through. It's the difference between trying to wash dishes in a sink full of plates versus having room to actually move things around and scrub them clean. The fluid dynamics are fascinating. The cerebrospinal fluid doesn't just passively seep through the brain, it's actively pumped by the pulsation of arteries. Every heartbeat sends a wave of pressure through the brain's blood vessels, and this wave helps drive the cerebrospinal fluid through the tissue. It's a brilliant bit of biological engineering, using the cardiovascular system as a pump for the brain's cleaning system. But there's more to this story. The glymphatic system doesn't just randomly wash away everything in its path. It shows a preference for certain types of waste, particularly the proteins associated with neurodegenerative diseases. Amyloid beta, the protein that forms plaques in Alzheimer's disease, is cleared twice as fast during sleep as during wakefulness. It's as if the cleaning system knows exactly what garbage is most important to remove. The discovery of the glymphatic system has revolutionized our understanding of why we sleep. For decades, sleep was one of biology's most enduring mysteries. Every animal sleeps, or does something similar. Even jellyfish, which have no brain, show sleep-like states. Fruit flies sleep, worms sleep. Sleep is so universal, so necessary, that animals will risk predation and starvation to get it. But why? From an evolutionary perspective, sleep seems like a terrible idea. You're unconscious, vulnerable, unable to eat, unable to mate, unable to defend yourself. Natural selection should have eliminated the need for sleep, or at least reduced it to a bare minimum. Yet most animals spend a third or more of their lives asleep. The glymphatic system provides at least part of the answer. Sleep isn't just rest, it's active maintenance. Without it, toxic metabolic waste would accumulate in the brain until neurons began to malfunction and die. It's not that sleep is a luxury that evolution couldn't eliminate. It's that sleep is so fundamentally necessary that evolution built our entire biology around accommodating it. Consider what happens when you don't sleep. After just one night of sleep deprivation, you can measure increased levels of amyloid beta in the brain and cerebrospinal fluid. The protein that's associated with Alzheimer's disease starts accumulating after missing just one night of sleep. After several nights, tau proteins, the other major culprit in Alzheimer's, also begin to increase. This isn't just correlation, it's causation. Researchers have shown that disrupting the glymphatic system in animals leads to accumulation of these toxic proteins and eventually to neurodegeneration. Conversely, enhancing glymphatic flow can accelerate the clearance of these proteins and potentially protect against neurodegenerative disease. The implications for human health are staggering. We're in the midst of an Alzheimer's epidemic. By some estimates, someone develops Alzheimer's disease every 65 seconds in the United States alone. By 2050, the number of people with Alzheimer's is projected to triple. We've spent billions on drug development, trying to find ways to clear amyloid beta from the brain or prevent its accumulation. But what if the answer isn't a drug? What if it's something as simple and as difficult as getting better sleep? The relationship between sleep and Alzheimer's appears to be bidirectional. Poor sleep leads to accumulation of amyloid beta and tau, but accumulation of these proteins also disrupts sleep. It's a vicious cycle. The less you sleep, the more toxic proteins accumulate. The more toxic proteins accumulate, the worse you sleep. Eventually, the system breaks down entirely. This might explain one of the cruel ironies of Alzheimer's disease. It often begins with sleep disturbances years or even decades before memory problems become apparent. The disease might actually start as a failure of the brain's cleaning system, with sleep disruption being both an early symptom and a contributing cause. But Alzheimer's isn't the only condition linked to glymphatic dysfunction. Parkinson's disease, chronic traumatic encephalopathy, CTE, and other neurodegenerative conditions all involve the accumulation of misfolded proteins in the brain. In each case, the glymphatic system's failure to clear these proteins might be a crucial factor. Even beyond neurodegeneration, the glymphatic system has implications for everyday brain function. That foggy feeling after a poor night's sleep, that might be literal metabolic waste clouding your neural function. The clarity that comes with a good night's rest, that's your brain, actually, physically cleaner than it was the night before. The glymphatic system also helps explain the mysterious relationship between sleep position and brain health. The system works most efficiently when you sleep on your side, particularly your right side. Back sleeping is less efficient, and stomach sleeping is the least efficient. This isn't just about comfort or preventing snoring, it's about the physics of fluid flow through your brain. When you lie on your side, gravity helps cerebrospinal fluid flow through the brain's drainage pathways. The lateral position also seems to open up certain channels more effectively. It's fascinating to note that most animals naturally sleep on their sides. Humans are unusual in our variety of sleep positions, and our preference for back sleeping might be contributing to our vulnerability to neurodegenerative disease. The timing of sleep matters too. The glymphatic system is most active during deep, slow-wave sleep, which occurs primarily in the first half of the night. This is when brain cells shrink the most, when cerebrospinal fluid flow is highest, and when the most waste is cleared. Those first few hours of sleep might be the most important for brain cleaning. This has implications for how we structure our sleep. Many people think they can get by with less sleep during the week and catch up on weekends. But if the first few hours of sleep are crucial for brain cleaning, then consistently cutting sleep short might mean consistently missing the most important cleaning cycles. It's like always leaving the dishwasher half finished. Eventually, the dirty dishes pile up. The type of sleep matters as well. Deep sleep decreases with age, which might partially explain why aging is the biggest risk factor for Alzheimer's disease. Certain medications, alcohol, and sleep disorders can all reduce the amount of deep sleep you get, potentially compromising glymphatic function. Even the temperature matters. The glymphatic system works more efficiently at cooler temperatures, which might be why we naturally cool down during sleep, and why a cool bedroom promotes better sleep. It's not just comfort, it's optimization of your brain's cleaning system. But here's where the story takes an even more intriguing turn. The glymphatic system isn't just about cleaning. It might also be involved in distributing beneficial substances throughout the brain. During sleep, the same channels that carry away waste also distribute growth factors, nutrients, and signaling molecules throughout the brain tissue. It's not just a sewage system. It's also a delivery system. This might help explain why sleep is so important for memory consolidation and learning. When you learn something new during the day, your neurons form new connections and strengthen existing ones. But these changes require proteins and other molecules to be synthesized and delivered to exactly the right spots. The glymphatic system, active during sleep, might be the distribution network that makes this possible. This could explain why sleeping on it really does help with problem solving and creativity. It's not just that your unconscious mind is working on the problem, it's that your brain is literally physically reorganizing itself, with the glymphatic system facilitating the delivery of materials needed for neural remodeling. Recent research has also suggested that the glymphatic system might be involved in distributing neurotransmitters and neuromodulators throughout the brain. These chemicals don't just affect the neurons they're released near, they can have widespread effects if distributed through the cerebrospinal fluid. Sleep might be when your brain rebalances its chemical environment, resetting neurotransmitter levels for the next day. There's even evidence that the glymphatic system might play a role in immune function. The brain was long thought to be immune privileged, isolated from the body's immune system. But recent discoveries have shown that the brain does have immune connections, and the glymphatic system might be how immune signals and cells move through brain tissue. So, tonight, as you prepare for sleep, remember that you're not just resting, you're about to undergo one of the most important biological processes of your life. Your brain is preparing to transform itself, to shift from the narrow, busy streets of wakefulness to the wide, flowing channels of sleep. In a few hours, as you drift off, your brain cells will begin to shrink. The spaces between them will open up. Cerebrospinal fluid will begin to flow through your brain tissue, carrying away the metabolic waste that accumulated during your day. Amyloid beta proteins will be swept away. Tau proteins will be cleared. The fog of metabolic waste will lift. Your astrocytes, those star-shaped cells once thought to be mere support structures, will manage this incredible process, their aquaporin 4 channels opening and closing like tiny gates, controlling the flow of fluid through your brain. Your arteries will pulse with each heartbeat, driving the cleaning fluid through your tissue. Your glymphatic system will hum with activity, all while you're completely unconscious of its work. This isn't just maintenance, it's renewal. Every night, your brain gets a fresh start. Every morning, you wake with a cleaner, clearer brain than you had the night before. The thoughts you think, the memories you form, the decisions you make, all are made possible by this nightly cleaning. It's humbling to think that we've only known about this system for about a decade. For all of human history, we've been sleeping without knowing why, trusting our bodies to do something essential without understanding what it was. Now we know every night, we undergo a biological restoration that's as essential to our survival as eating or breathing. So sleep well tonight, knowing that your brain's cleaning crew is ready to begin their shift. They've been waiting all day for you to close your eyes, to let your thoughts quiet, to allow your brain cells to relax and shrink. They're ready to flood your brain with cleansing fluid, to wash away the day's debris, to prepare you for tomorrow. This is the gift of sleep, not just rest, but renewal. Not just dreams, but cleaning. Not just unconsciousness, but a highly orchestrated biological process that keeps your brain healthy and functional. Sweet dreams. And remember, while you sleep, your brain's night shift is hard at work, keeping the most complex structure in the known universe clean and clear for another day of consciousness. But let's dive deeper into why evolution developed this peculiar system. Why didn't our brains evolve to clean themselves continuously? Why dedicate a third of our lives to unconscious maintenance? The answer lies in the fundamental constraints of biology and physics. The brain faces an impossible choice: be good at thinking or be good at cleaning, but not both simultaneously. This is because the same physical spaces that need to be tight for efficient neural communication need to be open for efficient waste clearance. Think about it from an engineering perspective. If you were designing a computer, you'd want the circuits close together for fast processing, but you'd also need space for cooling systems and maintenance access. In machines, we solve this by building in dedicated spaces for both, but the brain doesn't have that luxury. It's constrained by the skull, by energy limitations, and by the need to pack 86 billion neurons and their supporting cells into about 1.4 liters of space. Evolution's solution was temporal separation rather than spatial separation. Instead of having dedicated cleaning channels that would take up valuable real estate and reduce neural density, the brain uses the same spaces for different purposes at different times. During the day, these spaces are optimized for neural communication. At night, they're optimized for waste clearance. This is a remarkably elegant solution, but it comes with a cost: vulnerability. Every animal must sleep, must enter a state of unconsciousness and vulnerability to maintain their brain. This tells us something profound about the importance of brain cleaning. It's so crucial that evolution couldn't find a way around it. Despite millions of years of selection pressure, consider the alternatives that evolution might have tried. Why not just have a bigger skull with more room for dedicated cleaning channels? Because bigger brains require more energy, and human babies already have such large heads that childbirth is dangerous and limiting. Why not clean different brain regions at different times while staying awake? Because consciousness seems to require global brain integration. You can't shut down parts without affecting the whole. The evolution of sleep and the glymphatic system might also explain some puzzling aspects of brain evolution. Mammals and birds, the two groups with the most complex brains, also have the most developed sleep patterns, including distinct stages like REM and slow-wave sleep. Perhaps this isn't coincidence. Perhaps complex brains require complex cleaning systems. We live in an age that seems almost designed to sabotage the glymphatic system. Artificial light extends our waking hours. Smartphones and screens keep our brains in a state of alertness late into the night. Caffeine blocks the adenosine receptors that help trigger sleepiness. Alcohol disrupts sleep architecture. Stress hormones like cortisol interfere with the normal sleep-wake cycle. Consider the average modern evening. You're exposed to bright, blue-enriched light from screens until moments before trying to sleep. This light suppresses melatonin production and tells your brain it's still daytime. You might have had caffeine in the afternoon, which has a half-life of 5 or 7 hours, meaning it's still affecting your brain at bedtime. You might have a glass of wine to help you sleep, not knowing that alcohol disrupts the deep sleep when glymphatic cleaning is most active. Then there's the temperature issue. Modern homes are often kept warm at night for comfort, but the glymphatic system works best when the brain is cool. Our ancestors, sleeping in naturally cooling environments as night fell, had an advantage we've eliminated with central heating. The position problem is another modern issue. We sleep on soft mattresses that allow us to stay in one position all night, often on our backs, the worst position for glymphatic drainage. Our ancestors, sleeping on harder surfaces, naturally changed positions more frequently, potentially optimizing drainage throughout the night. Work schedules compound the problem. Shift work, jet lag and social jet lag, the mismatch between our natural sleep timing and social obligations, all disrupt the circadian rhythms that coordinate the glymphatic system. When you force yourself to wake with an alarm, you might be interrupting crucial cleaning cycles. Even our diet affects the glymphatic system. High-fat diets have been shown to impair glymphatic function. Chronic inflammation, often driven by processed foods and sedentary lifestyles, can damage the astrocytes that manage the cleaning system. Obesity is associated with reduced slow-wave sleep, the phase when cleaning is most active. The consequences of impaired glymphatic function extend far beyond Alzheimer's disease. Let's explore the growing list of conditions that might be at least partially diseases of inadequate brain cleaning. Parkinson's disease involves the accumulation of alpha-synuclein proteins in neurons. Like amyloid beta in Alzheimer's, alpha-synuclein is normally cleared by the glymphatic system. Patients with Parkinson's often have sleep disturbances years before motor symptoms appear. Could the disease begin with glymphatic dysfunction? Chronic traumatic encephalopathy, CTE, the disease affecting athletes and military personnel with repeated head injuries, involves the accumulation of tau proteins. Head injuries have been shown to impair glymphatic function, sometimes permanently. Each concussion might damage the brain's ability to clean itself, leading to progressive accumulation of toxic proteins. Multiple sclerosis, an autoimmune disease affecting the brain and spinal cord, might also involve glymphatic dysfunction. The system is responsible for clearing inflammatory molecules from the brain. When it fails, inflammation might persist, contributing to the immune attack on myelin that characterizes MS. Even migraine headaches might be related to glymphatic function. Some researchers propose that migraines represent a state of impaired glymphatic clearance, with metabolic waste accumulating until it triggers the pain and neurological symptoms of an attack. This might explain why many migraines are triggered by sleep deprivation and relieved by sleep. Depression and anxiety have also been linked to glymphatic dysfunction. Sleep disturbances are both symptoms and potential causes of mood disorders. The accumulation of metabolic waste might affect neurotransmitter function, contributing to the chemical imbalances associated with depression. Understanding the glymphatic system opens up entirely new avenues for treating and preventing neurological diseases, rather than developing drugs to break down amyloid beta after it accumulates. What if we could enhance the brain's natural cleaning system? Some approaches are already being tested. This appears untamed, Nader said. Sleep medications that specifically enhance slow-wave sleep might boost glymphatic function. Devices that use sound or electrical stimulation to deepen sleep are showing promise. Even simple interventions like sleeping position training might help. More exotic approaches are on the horizon. What if we could temporarily enlarge the spaces between brain cells while awake, allowing cleaning to occur without sleep? What if we could enhance cerebrospinal fluid production or flow? What if we could genetically modify astrocytes to be more efficient at managing the glymphatic system? There's even research into artificial cerebrospinal fluid that might be better at dissolving and carrying away protein aggregates. Imagine going to a clinic for a brain wash, having your cerebrospinal fluid replaced with an enhanced version that supercharges the cleaning process. Some researchers are exploring ways to monitor glymphatic function in living humans. Currently, we can only observe the system directly in animals or indirectly in humans through MRI. But new techniques might allow us to measure how well someone's brain is cleaning itself, potentially identifying problems before symptoms appear. The discovery of the glymphatic system has philosophical implications that extend beyond medicine. It fundamentally changes how we think about consciousness, identity, and the nature of thought itself. If our thoughts and memories are physically affected by the accumulation and clearance of metabolic waste, what does that say about the nature of consciousness? Are we different people in the evening, when our brains are full of metabolic debris, than we are in the morning after cleaning? Is the clarity we feel after good sleep not just metaphorical but literal? Are thoughts actually less obstructed by molecular waste? This also raises questions about personal responsibility and free will. If someone makes poor decisions when sleep deprived, are they fully responsible? Their brain is literally dirtier, their neurons swimming in metabolic waste. Should we think about sleep deprivation the way we think about intoxication, a state that impairs judgment and decision-making? There's also something profound about the fact that we must become unconscious to maintain consciousness. We must give up our awareness to preserve our ability to be aware. It's a fundamental vulnerability built into the nature of consciousness itself, at least as it exists in biological beings. Understanding the glymphatic system should trigger a cultural revolution in how we think about sleep. For too long we've treated sleep as wasted time, something to be minimized in the pursuit of productivity. Sleep when you're dead has been a rallying cry of the ambitious. But now we know that skipping sleep is literally leaving metabolic waste in your brain. It's like refusing to take out the garbage, letting it pile up day after day. Would we admire someone who boasted about never cleaning their house? Why do we admire those who boast about never cleaning their brain? We need to reconceptualize sleep as active maintenance, not passive rest. Just as we wouldn't skip brushing our teeth to save time, we shouldn't skip sleep to be more productive. The short-term gains are offset by long-term losses in cognitive function and health. This is particularly important for certain professions. Medical residents, who traditionally work extreme hours with minimal sleep, are literally damaging their brains during training. The same is true for military personnel, emergency responders, and others in demanding fields. We're asking people to perform critical tasks with brains full of metabolic waste. Schools, too, need to reconsider their approach. Early start times for teenagers, whose circadian rhythms naturally shift later, mean we're educating students whose brains haven't been properly cleaned. Is it any wonder that academic performance improves when schools start later? So how can you optimize your own glymphatic system? Based on current research, here are evidence-based strategies for better brain cleaning. First, prioritize sleep duration. Most adults need 7 mining hours, and cutting this short means cutting cleaning cycles. Think of it as a dishwasher. You need to run the full cycle for clean dishes. Second, focus on sleep quality, particularly deep sleep. Keep your bedroom cool, around 65 to 68 degrees Fahrenheit, or 18 to 20 degrees Celsius, dark and quiet. These conditions promote the deep, slow-wave sleep when glymphatic activity peaks. Third, consider your sleep position. Side sleeping, particularly on your right side, appears optimal for glymphatic drainage. If you're a back sleeper, even a slight elevation or turning can help. Fourth, maintain regular sleep schedules. The glymphatic system, like all biological processes, follows circadian rhythms. Irregular sleep confuses these rhythms and reduces cleaning efficiency. Fifth, Avoid alcohol and sleep medications that suppress deep sleep. While they might help you fall asleep, they can actually impair the cleaning process. Sixth, exercise regularly. Physical activity has been shown to enhance glymphatic function, possibly by improving the health of astrocytes and blood vessels. Finally, manage stress. Chronic stress and the associated cortisol release can impair both sleep quality and glymphatic function. Meditation, therapy, or other stress management techniques aren't just good for your mind, they're good for your brain's cleaning system. As you prepare for sleep tonight, remember that you're about to undergo the ultimate maintenance procedure. Your brain, that 3-pound universe of consciousness, is about to transform itself into a self-cleaning organ. The astrocytes are ready. There are aquaporin 4 channels primed to open. The cerebrospinal fluid is waiting to flow. The metabolic waste of your day, every thought, every emotion, every decision, has left its molecular residue, and now it's time for it to be washed away. This isn't just biology, it's poetry. The fact that consciousness requires unconsciousness, that clarity requires cleaning, that thoughts themselves produce physical waste that must be removed. These are profound truths about the nature of existence. You are not just a mind, you are a biological being whose thoughts depend on molecular processes, whose consciousness emerges from cells and fluids and proteins. And every night, this biological machinery must be maintained, cleaned, restored. So sleep well, knowing that your brain's night shift is about to begin their crucial work. They don't get recognition or applause. You'll never consciously experience their labor, but without them, without this nightly cleaning, consciousness itself would be impossible. Sweet dreams, and remember, while you rest, your brain's secret cleaning crew is hard at work, preparing you for another day of thought, emotion, and awareness. They are the unsung heroes of your mental life, the silent guardians of your cognitive health, the night shift that makes the day shift possible. Tomorrow, you'll wake with a cleaner brain, ready to face the world anew. But tonight, let yourself sink into sleep, knowing that one of the most important processes of your life is about to begin. The cleaning crew is ready. Close your eyes and let them work. Let's delve deeper into the actual mechanics of how your brain transforms into a washing machine each night, because the process is more intricate and beautiful than we've yet described. When you begin to fall asleep, it doesn't happen all at once. Your brain goes through a carefully orchestrated shutdown sequence, like a complex factory preparing for maintenance. First, your thalamus, the brain's sensory relay station, begins to close its gates, reducing the flow of information from the outside world. Your cortex, the outer layer, where conscious thought occurs, starts to synchronize its activity into slow rolling waves. These slow waves aren't just electrical patterns, they're physical pumps. Each wave represents millions of neurons firing together, then falling silent together. This synchronized activity creates pressure waves that push cerebrospinal fluid through the brain tissue. Imagine squeezing and releasing a sponge rhythmically. That's essentially what your brain is doing to itself during deep sleep. The astrocytes, those star-shaped cells we mentioned earlier, undergo a remarkable transformation during this process. During wakefulness, they're swollen with activity, their end feet pressed tightly against blood vessels, maintaining the blood-brain barrier. But as sleep deepens, they literally change shape. They retract slightly, creating gaps, channels, highways for fluid to flow. The aquaporin 4 channels in these astrocytes are particularly fascinating. These proteins form pores in cell membranes that allow water to pass through. They're arranged in highly organized arrays, called orthogonal arrays of particles, which sounds like something from science fiction but is actually visible under electron microscopy. These arrays are concentrated at the astrocyte end feet, precisely where they're needed to regulate fluid flow. During wakefulness, these channels are relatively inactive, but during sleep, they open wide, increasing water permeability by up to 20-fold. It's like opening thousands of tiny faucets throughout your brain simultaneously. The precision of this system is breathtaking. Millions of channels opening in concert, creating a flood of cleaning fluid exactly when and where it's needed. The waste products being cleared by the glymphatic system tell us something profound about the nature of thought itself. Every time you think a thought, form a memory, or feel an emotion, you're literally creating physical waste products that must be removed. Consider what happens at the molecular level when a neuron fires. The cell must pump ions across its membrane, requiring ATP, the cellular energy currency. Breaking down ATP produces adenosine, a waste product that accumulates during wakefulness. Adenosine is what makes you feel sleepy. It's literally the exhaust fume of consciousness. Caffeine works by blocking adenosine receptors, preventing you from feeling this accumulation, but the waste is still there, still building up. Protein synthesis is another major source of brain waste. Every time you learn something new, neurons must produce new proteins to strengthen synapses and form memories. This process inevitably produces misfolded proteins, cellular origami that went wrong. During wakefulness, these misfolded proteins accumulate. During sleep, they're cleared away. The brain also produces reactive oxygen species, free radicals, as a byproduct of its enormous energy consumption. These molecules are like cellular rust, damaging proteins, lipids, and even DNA, if not quickly neutralized. The glymphatic system helps flush these out, along with the damaged molecules they create. Even neurotransmitters become waste products. After serotonin, dopamine, or other signaling molecules do their job, they must be broken down and cleared away. Their metabolites, the broken down fragments, are removed by the glymphatic system. In a very real sense, yesterday's happiness, yesterday's motivations, yesterday's fears must be physically washed out of your brain to make room for today's experiences. Let's delve deeper into the actual mechanics of how your brain transforms into a washing machine each night, because the process is more intricate and beautiful than we've yet described. When you begin to fall asleep, it doesn't happen all at once. Your brain goes through a carefully orchestrated shutdown sequence, like a complex factory preparing for maintenance. First, your thalamus, the brain's sensory relay station, begins to close its gates, reducing the flow of information from the outside world. Your cortex, the outer layer where conscious thought occurs, starts to synchronize its activity into slow rolling waves. These slow waves aren't just electrical patterns, they're physical pumps. Each wave represents millions of neurons firing together, then falling silent together. This synchronized activity creates pressure waves that push cerebrospinal fluid through the brain tissue. Imagine squeezing and releasing a sponge rhythmically. That's essentially what your brain is doing to itself during deep sleep. The astrocytes, those star-shaped cells we mentioned earlier, undergo a remarkable transformation during this process. During wakefulness, they're swollen with activity, their end feet pressed tightly against blood vessels, maintaining the blood-brain barrier. But as sleep deepens, they literally change shape. They retract slightly, creating gaps, channels, highways for fluid to flow. The aquaporin 4 channels in these astrocytes are particularly fascinating. These proteins form pores in cell membranes that allow water to pass through. They're arranged in highly organized arrays called orthogonal arrays of particles, which sounds like something from science fiction, but is actually visible under electron microscopy. These arrays are concentrated at the astrocyte end feet, precisely where they're needed to regulate fluid flow. During wakefulness, these channels are relatively inactive, but during sleep, they open wide, increasing water permeability by up to 20-fold. It's like opening thousands of tiny faucets throughout your brain simultaneously. The precision of this system is breathtaking. Millions of channels opening in concert, creating a flood of cleaning fluid exactly when and where it's needed. The waste products being cleared by the glymphatic system tell us something profound about the nature of thought itself. Every time you think a thought, form a memory, or feel an emotion, You're literally creating physical waste products that must be removed. Consider what happens at the molecular level when a neuron fires. The cell must pump ions across its membrane, requiring ATP, the cellular energy currency. Breaking down ATP produces adenosine, a waste product that accumulates during wakefulness. Adenosine is what makes you feel sleepy. It's literally the exhaust fume of consciousness. Caffeine works by blocking adenosine receptors, preventing you from feeling this accumulation, but the waste is still there, still building up. Protein synthesis is another major source of brain waste. Every time you learn something new, neurons must produce new proteins to strengthen synapses and form memories. This process inevitably produces misfolded proteins, cellular origami that went wrong. During wakefulness, these misfolded proteins accumulate. During sleep, they're cleared away. The brain also produces reactive oxygen species, free radicals, as a byproduct of its enormous energy consumption. These molecules are like cellular rust, damaging proteins, lipids, and even DNA, if not quickly neutralized. The glymphatic system helps flush these out, along with the damaged molecules they create. Even neurotransmitters become waste products. After serotonin, dopamine, or other signaling molecules do their job, they must be broken down and cleared away. Their metabolites, the broken down fragments, are removed by the glymphatic system. In a very real sense, yesterday's happiness, yesterday's motivations, yesterday's fears must be physically washed out of your brain to make room for today's experiences. The glymphatic system didn't evolve in isolation. It's part of a much older story about how complex brains arose and why sleep became mandatory for consciousness. The earliest nervous systems, in creatures like jellyfish and hydras, didn't need elaborate cleaning systems. These simple neural networks could clear waste directly into the surrounding water. But as nervous systems became more complex and centralized, waste clearance became a problem. The evolution of the blood-brain barrier, probably around 500 million years ago, created both a solution and a new problem. It protected delicate neural tissue from toxins and pathogens in the blood, but it also isolated the brain from the body's cleaning systems. Evolution's answer was to repurpose the cerebrospinal fluid system, which originally evolved for buoyancy and protection, into a cleaning mechanism. But this created a new constraint. The cleaning system required space that was also needed for neural processing. The solution, temporal segregation through sleep, may have been one of the key innovations that allowed complex brains to evolve. Without sleep, without a way to clean metabolic waste, large brains would poison themselves with their own byproducts. This might explain one of the mysteries of evolution. Why did complex cognition evolve independently in mammals and birds but not in other groups? Both mammals and birds have elaborate sleep patterns with distinct stages. Both have glymphatic-like systems, though birds' version is slightly different and less well studied. Perhaps the evolution of efficient brain cleaning was a prerequisite for the evolution of complex cognition. Looking even deeper, we can see how sleep cleaning might have shaped the very nature of consciousness. The need to go offline for cleaning might be why consciousness has the particular character it does: unified, integrated, but interruptible. A conscious system that couldn't turn off would accumulate waste until it failed. So consciousness evolved to be episodic, punctuated by periods of unconscious maintenance. Some researchers are beginning to explore whether quantum mechanical processes might play a role in the glymphatic system. This isn't the mystical quantum consciousness of New Age thinking, but serious investigation into whether quantum effects influence fluid flow through the incredibly tiny spaces in the brain. Water molecules flowing through the narrow channels between brain cells behave differently than bulk water. They form ordered structures, almost crystalline arrangements, that have unique properties. Some physicists suggest these ordered water structures might exhibit quantum coherence, synchronized quantum states that could affect how waste molecules are transported. The aquaporin 4 channels themselves are small enough that quantum effects might be significant. Water molecules passing through these channels do so in single file, one at a time. At this scale, quantum tunneling, where particles pass through barriers they shouldn't classically be able to cross, might play a role in the efficiency of water transport. There's even speculation that the electromagnetic fields generated by synchronized neural activity during sleep might influence the quantum properties of water in the brain, potentially enhancing or directing the flow of cerebrospinal fluid. While this remains highly speculative, it opens fascinating possibilities for understanding and potentially manipulating the cleaning process. How does the glymphatic system change throughout our lives? This question has profound implications for understanding both development and aging. In infants, the glymphatic system is incredibly active. Babies sleep up to 17 hours a day, and much of this is deep sleep with high glymphatic activity. This makes sense. The developing brain is producing new neurons, forming countless new connections, and generating enormous amounts of metabolic waste. The infant brain is like a construction site that needs constant cleanup to function. The glymphatic system might also play a crucial role in brain development itself. The distribution of growth factors, the removal of excess neurotransmitters, the clearing of cellular debris from pruned synapses, all of these developmental processes depend on efficient waste clearance and molecular distribution. During childhood and adolescence, sleep patterns change dramatically, and so does glymphatic function. The reduction in sleep duration as children grow might reflect reduced need for brain cleaning as the pace of brain development slows. But the teenage years bring new challenges: hormonal changes, rapid brain remodeling, and shifted circadian rhythms all affect glymphatic function. The teenage brain undergoes massive restructuring, particularly in the prefrontal cortex. Old synapses are pruned away, new ones are formed, white matter increases as neurons are myelinated. All of this produces waste that must be cleared. This might partially explain why teenagers need more sleep than younger children. Their brains are undergoing renovation and need extra cleaning time. In young adulthood, the glymphatic system reaches peak efficiency. The brain has finished developing, the cleaning system is optimized, and sleep patterns are ideally regular. This is when the system works as evolution intended, regular nightly cleaning maintaining optimal brain function. But then aging begins to take its toll. Starting around age 30, slow-wave sleep begins to decline. By age 70, some people have lost up to 90% of their deep sleep. This dramatic reduction in the sleep stage when glymphatic cleaning is most active might be one of the key factors in age-related cognitive decline. The astrocytes themselves age, becoming less efficient at managing fluid flow. The aquaporin 4 channels become less organized, scattering from their optimal positions at astrocyte end feet. Blood vessels become stiffer, reducing the pulsatile flow that helps drive cerebrospinal fluid through the brain. Even the production of cerebrospinal fluid decreases with age, from about 600 milliliters per day in young adults to perhaps 300 milliliters in the elderly. It's as if the brain's washing machine is running with less water, weaker pumps and clogged filters. One of the most powerful ways to enhance glymphatic function isn't about sleep at all, it's about exercise. Physical activity has profound effects on the brain's cleaning system, both immediate and long-term. During exercise, your heart rate increases, driving stronger pulsations through cerebral blood vessels. These enhanced pulsations can improve cerebrospinal fluid flow even hours after exercise ends. It's like giving your brain's cleaning system a turbo boost that lasts well into the night. Exercise also triggers the production of brain-derived neurotrophic factor, BDNF, sometimes called miracle grow for the brain. BDNF not only promotes the growth of new neurons and synapses, but also supports the health of astrocytes, the cells that manage the glymphatic system. Regular exercisers have healthier, more efficient astrocytes, which means better brain cleaning. The type of exercise matters. Aerobic exercise, running, swimming, cycling, seems particularly beneficial for glymphatic function. The rhythmic increase in heart rate and blood pressure creates optimal conditions for cerebrospinal fluid flow. But even resistance training helps. possibly by improving vascular health and astrocyte function. The timing of exercise also influences its effects on the glymphatic system. Morning exercise can help clear any residual metabolic waste from incomplete sleep cleaning. Evening exercise, if not too late, can prime the glymphatic system for more efficient cleaning during subsequent sleep. There's also emerging evidence that certain types of breathing exercises can enhance glymphatic flow. Deep, rhythmic breathing creates pressure changes in the chest that are transmitted to the brain, potentially driving cerebrospinal fluid movement. Some yogic breathing practices, developed thousands of years ago, might have unknowingly been optimizing brain cleaning. What you eat profoundly affects how well your brain cleans itself. The glymphatic system, like all biological systems, is influenced by nutrition, and certain dietary patterns can either enhance or impair its function. Omega-3 fatty acids, particularly DHA found in fish oil, are crucial for maintaining the flexibility of cell membranes, including those of astrocytes. Flexible membranes allow astrocytes to change shape more easily during the sleep-wake cycle, potentially improving the opening and closing of fluid channels. Populations that consume high amounts of omega-3 SAS have lower rates of Alzheimer's disease, possibly due in part to better glymphatic function. Antioxidants protect the glymphatic system from damage. The astrocytes and neurons involved in brain cleaning are vulnerable to oxidative stress. Compounds like vitamin E, vitamin C, and polyphenols from berries, green tea, and dark chocolate can protect these cells, maintaining their efficiency as we age. But perhaps most importantly, when you eat matters as much as what you eat. Time-restricted eating, limiting food consumption to an 8-10-hour window, has been shown to enhance glymphatic function. This eating pattern aligns with our circadian rhythms, optimizing the metabolic conditions for brain cleaning during sleep. Late-night eating is particularly problematic. Digestion requires significant blood flow and metabolic activity, which can interfere with the brain's transition to cleaning mode. Eating close to bedtime can reduce slow-wave sleep and impair glymphatic function. Our ancestors who couldn't raid the refrigerator at midnight had an advantage we've lost. Hydration also plays a crucial role. The glymphatic system is, fundamentally, a fluid-based system. Dehydration reduces cerebrospinal fluid production and can impair flow through brain tissue. But timing matters here too. Drinking large amounts of fluid right before bed can disrupt sleep with bathroom trips. The key is maintaining good hydration throughout the day. Alcohol deserves special mention as a glymphatic disruptor. While a nightcap might help you fall asleep, alcohol profoundly disrupts sleep architecture, particularly suppressing REM sleep and fragmenting slow-wave sleep. Regular alcohol consumption is associated with reduced glymphatic function and increased accumulation of amyloid beta. Chronic stress might be one of the most significant threats to glymphatic function in modern life. The relationship between stress, sleep, and brain cleaning forms a triangle of interconnected effects, each influencing the others. Stress hormones, particularly cortisol, directly interfere with the glymphatic system. Cortisol affects astrocyte function, potentially impairing their ability to manage fluid flow. It also fragments sleep, reducing the continuous periods of slow-wave sleep needed for efficient cleaning. But the relationship goes deeper. Chronic stress causes inflammation in the brain, and inflammatory molecules can damage the delicate structures of the glymphatic system. Inflamed astrocytes don't function properly. Inflammatory cytokines disrupt the blood-brain barrier, potentially interfering with the controlled flow of fluids necessary for brain cleaning. Poor glymphatic function, in turn, can worsen stress responses. When metabolic waste accumulates in the brain, it affects neurotransmitter function and neural communication. The prefrontal cortex, crucial for emotional regulation, is particularly vulnerable to the effects of metabolic waste accumulation. A dirty brain is literally less capable of managing stress. This creates a vicious cycle. Stress impairs sleep. Poor sleep reduces glymphatic cleaning. Accumulated waste worsens stress responses, which further impairs sleep. Breaking this cycle requires addressing all three components: managing stress, improving sleep, and supporting glymphatic function. Meditation and mindfulness practices might help by reducing stress and potentially enhancing glymphatic function directly. Some studies suggest that experienced meditators have enhanced slow-wave sleep and more efficient brain cleaning. The deep relaxation achieved in meditation might create conditions similar to sleep in terms of glymphatic activation. We're on the verge of technological breakthroughs that could revolutionize how we enhance and monitor glymphatic function. These emerging technologies range from simple devices you could use at home to advanced medical interventions. Transcranial direct current stimulation, TDCS, involves applying weak electrical currents to the scalp to influence brain activity. Recent research suggests that specific TDCS protocols can enhance slow-wave sleep and potentially boost glymphatic function. Imagine a headband you wear to bed that optimizes your brain's cleaning cycles. Acoustic stimulation is another promising approach. Playing specific sounds or tones during slow-wave sleep can enhance the depth and duration of these crucial cleaning periods. These sounds are timed to coincide with the brain's natural slow waves, amplifying them like pushing a swing at just the right moment. Focused ultrasound, though still experimental, might be able to temporarily open the blood-brain barrier in controlled ways, potentially enhancing waste clearance. This could be particularly useful for removing accumulated proteins in people at risk for neurodegenerative diseases. Even more exotic approaches are being investigated. Some researchers are exploring whether magnetic fields could influence cerebrospinal fluid flow. Others are investigating drugs that specifically enhance astrocyte function or increase the expression of aquaporin 4 channels. Monitoring technology is advancing rapidly too. New MRI techniques can visualize glymphatic flow in living humans, though they're currently too expensive and cumbersome for regular use. But researchers are developing portable devices that might be able to assess glymphatic function through indirect measures like skull impedance or subtle changes in head circumference as cerebrospinal fluid volumes shift. The glymphatic system has implications that extend beyond individual health to society as a whole. We're beginning to understand that sleep deprivation isn't just a personal problem. It's a public health crisis with enormous social costs. Consider the workplace. When employees are sleep deprived, they're literally working with brains full of metabolic waste. Decision-making suffers, creativity decreases, errors increase. The economic cost of sleep deprivation in terms of lost productivity, workplace accidents, and poor decisions is estimated in the hundreds of billions annually. The medical profession ironically exemplifies this problem. Medical residents routinely work 24-hour shifts, making life and death decisions with brains that haven't been cleaned in over a day. Studies show that sleep-deprived residents make significantly more medical errors. We're asking people to perform at their peak while their brains are swimming in metabolic waste. Education is another domain where understanding the glymphatic system should drive policy changes. Early school start times mean millions of students are trying to learn with incompletely cleaned brains. Teenagers, whose circadian rhythms naturally shift later, are particularly affected. They're being asked to absorb and process complex information while their neurons are still bathed in yesterday's metabolic waste. The criminal justice system might also need to reconsider how it views sleep deprivation. If someone commits a crime while severely sleep deprived, their brain was literally impaired by accumulated metabolic waste. Should this be considered similar to intoxication? Should there be legal limits on how sleep-deprived someone can be while performing certain activities? Modern life has eliminated many environmental cues that once optimized our glymphatic function. Understanding what we've lost might help us reclaim better brain health. Temperature variation is one such lost cue. Our ancestors experienced significant temperature drops at night, which naturally cooled the brain and enhanced glymphatic function. Modern climate control keeps temperatures constant, eliminating this natural optimizer of brain cleaning. Darkness is another lost environmental factor. For millions of years, humans experienced true darkness at night. This profound darkness triggered melatonin release and set the stage for deep sleep. Modern light pollution means many of us never experience true darkness, potentially compromising our brain's cleaning cycles. Natural sounds might also play a role. The gentle rhythmic sounds of nature, wind, water, rustling leaves, might have helped entrain the slow waves of deep sleep. The harsh, irregular sounds of modern life, traffic, sirens, electronic beeps, disrupt these natural rhythms. Even the air we breathe has changed. Indoor air often has higher CO2 levels than outdoor air. Elevated CO2 can affect sleep quality and potentially impair glymphatic function. Our ancestors, sleeping in well-ventilated spaces or outdoors, breathed air that better supported brain cleaning. So, social environment has changed too. Humans evolved sleeping in groups, with shared sleep-wake cycles reinforced by social cues. Modern isolation, irregular schedules, and artificial lighting mean we've lost these social synchronizers of sleep patterns. The pharmaceutical industry is racing to develop drugs that enhance glymphatic function. These range from modifications of existing sleep aids to entirely novel compounds, targeting specific aspects of the cleaning system. Some researchers are investigating drugs that specifically enhance slow-wave sleep without the side effects of traditional sedatives. These might work by mimicking the natural neurochemicals that trigger deep sleep, or by enhancing the brain's response to these chemicals. Others are developing compounds that directly affect astrocyte function. These might increase the expression of aquaporin 4 channels, enhance the flexibility of astrocyte membranes, or optimize the positioning of channels at astrocyte end feet. There's particular interest in drugs that could temporarily enlarge the spaces between brain cells, allowing enhanced cleaning without requiring sleep. Imagine taking a pill that triggers a cleaning mode in your brain while you remain awake, though the safety and feasibility of this approach remain uncertain. Some existing drugs might be repurposed for glymphatic enhancement. Certain blood pressure medications, for instance, have been found to improve cerebrospinal fluid flow. Some anti-inflammatory drugs might protect the glymphatic system from damage. But pharmaceuticals aren't without risks. The glymphatic system is intricately connected to many other brain functions. Drugs that enhance cleaning might have unexpected effects on cognition, emotion, or other aspects of brain function. The history of medicine is littered with examples of drugs that solved one problem while creating others. Ancient contemplative practices might have been optimizing brain cleaning long before we knew the glymphatic system existed. Modern neuroscience is revealing surprising connections between meditation and glymphatic function. During deep meditation, brain waves shift toward patterns similar to those seen in slow-wave sleep. The default mode network, the brain's ego center, quiets down, potentially allowing for enhanced fluid flow through brain tissue. Some experienced meditators can even enter states where their brain waves are indistinguishable from deep sleep, while remaining conscious. Yoga nidra, or yogic sleep, is particularly interesting from a glymphatic perspective. This practice involves lying still and systematically relaxing the body while maintaining awareness. Brain scans show that yoga nidra can induce brain states similar to slow-wave sleep, potentially allowing for some degree of brain cleaning while conscious. Even simple breathing exercises might enhance glymphatic function. The pressure changes in the chest during deep breathing are transmitted to the brain through blood vessels and cerebrospinal fluid. Certain pranayama yogic breathing techniques create rhythmic pressure waves that might drive fluid through brain tissue. The mindfulness component of meditation might also indirectly support glymphatic function by reducing stress, improving sleep quality, and promoting the relaxation necessary for efficient brain cleaning. Regular meditators often report needing less sleep while feeling more refreshed, possibly because their meditation practice partially fulfills the brain cleaning function of sleep. The habits and patterns established in childhood might determine glymphatic function throughout life. This makes childhood sleep one of the most critical factors in long-term brain health. Children who consistently get inadequate sleep show differences in brain structure that persist into adulthood. The hippocampus, crucial for memory, is smaller in adults who were sleep-deprived as children. White matter integrity is compromised. These structural differences might reflect years of inadequate brain cleaning during critical developmental periods. Sleep disorders in childhood, such as sleep apnea, can have lifelong consequences for glymphatic function. The repeated interruptions in breathing disrupt slow-wave sleep, potentially impairing brain cleaning during crucial developmental years. Children with untreated sleep apnea show cognitive deficits that can persist even after the sleep disorder is resolved. The modern epidemic of childhood obesity might also be compromising glymphatic function in developing brains. Obesity is associated with inflammation, sleep-disordered breathing, and reduced slow-wave sleep, all factors that impair brain cleaning. Screen time is another modern threat to childhood glymphatic function. The blue light from screens suppresses melatonin, delays sleep onset, and reduces sleep quality. Children today are exposed to more artificial light than any generation in history, potentially compromising their brain cleaning from an early age. When we step back and look at the glymphatic system in the context of all biology, we see something profound. Evolution has prioritized brain cleaning above almost everything else. Consider what we sacrifice for sleep. We give up eating, mating, defending territory, all the activities that drive evolution. We become vulnerable to predation. We lose consciousness itself. Evolution doesn't make such trade-offs lightly. The fact that every animal with a complex brain must sleep tells us that brain cleaning is absolutely essential for neural function. The universality of sleep across the animal kingdom, despite its obvious disadvantages, is one of the strongest pieces of evidence for the critical importance of the glymphatic system. From the smallest shrew to the largest whale, from birds that sleep while flying to dolphins that sleep one hemisphere at a time, evolution has found ways to ensure brain cleaning happens. This prioritization extends to the molecular level. The genes involved in sleep and glymphatic function are highly conserved across species. The aquaporin 4 channels in your brain are remarkably similar to those in a mouse brain. The basic machinery of brain cleaning has been preserved across hundreds of millions of years of evolution. As we reach the end of our journey through the hidden world of brain cleaning, let's take a moment to appreciate the elegant symphony that plays out in your head every night. As you drift off to sleep tonight, imagine the transformation beginning. Your neurons, tired from a day of firing, begin to synchronize their activity. Waves of electrical activity roll across your cortex like waves on a beach. Your astrocytes, those unsung heroes of brain maintenance, begin their shape-shifting dance, opening channels for fluid to flow. Your blood vessels pulse with your heartbeat, but now each pulse drives a wave of cerebrospinal fluid through your brain tissue. This crystal-clear fluid, manufactured in chambers deep in your brain, begins its journey through the microscopic spaces between cells, picking up metabolic waste like a gentle stream carrying away leaves. Amyloid beta proteins, the villains of Alzheimer's disease, are swept from the crevices where they've accumulated during your waking hours. Tau proteins are bundled and carried away. The adenosine that made you sleepy is cleared. The free radicals that threaten cellular damage are neutralized and removed. Yesterday's neurotransmitters, their messages delivered, are broken down and washed away. This isn't just cleaning, it's renewal. Your brain is preparing itself for another day of consciousness, another day of thoughts and emotions and memories. Every night, you undergo a biological restoration, as essential as breathing, as fundamental as your heartbeat. We live in an age that has forgotten the importance of sleep, that treats it as an inconvenience to be minimized. But now we know better. We know that sleep is when the brain saves itself from itself, when consciousness pauses so that the machinery of consciousness can be maintained. The discovery of the glymphatic system is a reminder that we're still learning fundamental truths about our own biology. A decade ago, we didn't know this system existed. What other secrets does the sleeping brain hold? What other maintenance processes await discovery? As you close your eyes tonight, remember that you're not just resting, you're activating one of the most sophisticated cleaning systems in biology. Your brain is about to undergo a transformation as profound as any that occurs in nature, from thinking machine to washing machine and back again. Sweet dreams, and remember, while you sleep, trillions of cells work in concert to clean the most complex structure in the known universe. They don't ask for recognition or praise. They simply do their job, night after night, keeping your brain healthy and functional for another day of wonder. Tomorrow morning, when you wake with a clear head and fresh thoughts, take a moment to thank your glymphatic system, your brain's night shift, your cellular cleaning crew, the silent guardians of your consciousness. They've been working all night to give you a clean start to a new day. And perhaps, knowing what you now know about the importance of brain cleaning, you'll prioritize sleep, not as lost time but as an investment in your cognitive future. You'll go to bed, not reluctantly but gratefully, knowing that you're about to undergo a biological miracle that's been perfected over millions of years of evolution. The night shift is ready. Your brain's cleaning crew awaits. Close your eyes and let them work their magic.